Good morning, everybody. For some minutes, I would like to address the points that Wim just mentioned. My coordinates will be given at the end if you wish to keep in contact. The content of my presentation will be mainly three chapters. First concerning climate dynamics, second one concerning urban development dynamics, and as a match of the two previous one, the third chapter will be forthcoming challenges for construction. So first of all, here's a very simplistic view of the solar system with the Earth and the Sun, bright Sun. And all our system looks very simple because the Earth receives energy from the Sun and loses energy to the space, mainly through long-wave radiation. And in between, there is a very important layer, which is the atmosphere layer, where all the things happen. Well, I mean, all the things I will not develop today, but many energy and mass transfers. And the result of it is that the energy balance of the system results in a temperature, average temperature, which is favorable to life on Earth. If we now look at the factors that can influence this balance, this system is so simple that many people just try to understand it better, and we now know better and better the system and why the energy balance can be influenced. Among the factors, there are the Earth movements, which are known as the Milankovitch cycle, from the name of Milankovitch who made this work. Well, I will not develop it here in detail, but the distance plays and the inclination plays a role in the energy received by the Earth. The variation in solar radiation is also one influential factor. This variation can come from intrinsic factors. The Sun is more or less brilliant. And also from obstacles risen, for instance, from volcano eruptions. And greenhouse gases was the evidence of greenhouse gases. It plays an important role, was put in evidence at the end of the 19th century. And in the 19th century, and we now know through IPCC reports that the human activity plays an important role through this mechanism of greenhouse gas. I will not elaborate more today because all the auditors, I guess, know very well the work of IPCC, but the result is that we have probably to face some very changing climate in the future. Here is balance I will not comment on because everybody knows a lot about it. Let's now come to urban development dynamics. It's another important thing that we would like to develop today. Here is a graph showing the evolution of the world population from minus 65,000. The reference is this one. It also comes from a collaboration with the UN World Population Prospects. And here I pointed some important facts on this figure. First of all, the first cities were more or less likely in this area here some thousands of years ago. And we were now 1.7 billion in 1900. We are today 7 billion and expect to be 9 million at the end of this century. So there is a huge growth of a population. But in addition to that, we also must have a look at the share of the urban population. And this share of urban population is constantly growing. It was about 13% in the beginning of 20th century, here 25, here now 2005 recently, but 50%, and expected to grow to 60% in tomorrow morning. That means 2030. And in addition to that, another addition is the number of both large cities and megacities, large cities being from 5 to 10 million, and megacities more than 10 million. In 2011, there were about a bit more than 20 large cities and 40 megacities, and respectively, these figures are expected to be 37 and nearly 60 in 2000 in some years. So this illustrates the urban development dynamics I wanted to point out. If you now consider both the two challenges, the two dynamics are presented, It gives a way to present the forthcoming challenges for construction. They will result from a conjunction of different factors. First of all, sustainability issues, which is the topic of today, concern resources, including economy, of course, society issues too. The exposure increase, there are more people and more assets in exposed areas, and the evolution of the drivers' hazards, which are basically wind, precipitation, and temperature at the local scale. So this factor may become more or less intense, more or less frequent, resulting in some places more floods, more storms, maybe less storms too, less floods either, but things will change, and very likely to change. And there also a point I would like to mention, though it's not a very strong signal for today, but the emergence of new risks at local scale may be something we have to face in the future. For instance, the vectors for disease which will develop, we do not know locally, but will encounter in the future due to the changing climate conditions. So there is a question, how do we face such challenges? Wisely, many governments have agreed on the fact that GHG emissions are something we must mitigate. So here is a nice building which emits greenhouse gases, and the first reflex was to turn off the GHG tap. It was mainly made, but not only, by the improvement of thermal performances. This aimed to limit climate change. The changes I just mentioned before. But due to the inertia of the atmospheric system, whatever you do now, even if you reduce it to zero, something will happen. And what we have to face also to anticipate the climate change effects that may shake our built environment. And this legal small figure here allows introducing two main concepts, which are mitigation and adaptation. Mitigation of greenhouse gas emissions and adaptation to changing impacts. That being said, I would like just to give some example. I focus on the example of heat waves. I introduced first horizontal scale here that will now become vertical, temperature scale, and a horizontal scale, which is the heat wave duration from 0 to 40 days. And I introduced the first figure, which is a French situation. The record of two past heat waves, one in 1976 and one in 2003. And the disk here is proportional to the duration and the intensity of the heat wave. You see in 2003 was hotter than 1976, but the result was also more intense here in 2003. And in both cases, and mainly in 2003, an excess mortality was some tens of thousands over Europe. And there were also recorded huge structural damages, mainly on individual houses, which have shallow foundations. If we now look at the projections based on the IPCC scenarios, this is the work carried out by my French colleague of the Met Office in France. You see that the two previous heat waves are here now in a cloud of orange bubble, which are much bigger and much more numerous. And this cloud of bubbles, of course, depends on the scenario. In the worst case, it may be something like that, with the date of appearance here written. I will comment in detail. But what is really noticeable here in this figure is that if we emit a lot, we may have such situation. If we restrict emission, we may have a less worse situation. Based on this example of heat waves, we developed a specific study for the Paris area, funded by the town of Paris, and together with my colleagues of the French Met Office, Météo France. And here is a final result. This graph shows here an average temperature on the hottest part of the heat wave in August 2003, and just reflects the effects of some measures we have been simulating. The dotted curves here is the reference, such as recorded during the heat wave. And the colored curves down are referred to different scenarios. For instance, S1 here refers to a high albedo infrared emissivity, which would be the property of all the walls and roof surfaces in the town. Another example, S2, which is very close to the reference here, is concerns much important increase, 89% increase of green surfaces, but which is not watered. And the effect is very limited, if not nil. The two curves are just one over the other. And if you then consider S2 bis, here is the same green area, but water, and then the effect is slightly effect here. And if you water street surfaces, it's the blue one here. You also have some impact on the intensity, on the level of temperature, average temperature over the town, and from east to west according to this cross section. Here, these blue areas here are two main woods, important woods in the east, west and east of Paris. And if you add all this, you have S dot, which is the bottom line here. I will comment much more. If people are interested, they will contact me and we'll give all access to full reports. What is noticeable here is that water resource is a key issue. When no water, nearly no effect. So we have to think about it. So the two most efficient effects, if I dare say, are the high albedo S1 and water-related scenarios. So we look to have some means to mitigate the heat wave impact on intensity, not the heat wave intensity, excuse me, the urban heat wave intensity. But there are some pending questions. I just want to address some of them concerning with feasibility, credibility, acceptability, and maintenance. I present this according to my example, but we may also transfer this to any kind of natural hazards such as flood or wind. So feasibility, of course, there is a question of technical and economic feasibility. But as shown here, we'll have to arbitrate between surface use. Here's a picture of the Paris roofs as it is now. The dominant product is zinc here. This is not zinc, it's steel, but I took it as an example. Zinc is the most widespread material to cover roofs in Paris. If you choose to green it, it may look like that. To put photovoltaic cells, it may look like that. Or to use high albedo, it may look like that. Of course, high albedo products may not necessarily be white looking, but it's another question. Another question I would like to address is credibility. Decision makers will have to take measures, so it's important that the model used to assess the future of the perspective are credible. So it's important to validate model and to take time to do this. It may be made through experiments, measurement, and monitoring of some experimental solutions. The acceptability is also a key issue. Just look at the transformation, at the look of the city from the initial view to any of these views here. Well, it's not obvious to accept it, and also from both the point of view of the citizens, but also from the tourists that come to very strongly visited cities like Paris or other capitals. So we must, decision makers have also to address this point. Maintenance is not the last point; it's a very important point together, because in simulation very often we introduce initial conditions that reflect the maximum property. But as you know, the old products age and the performances, the initial performances, decrease or change with time. If you take this, for instance, with pollution, after some months or some years, it will become less reflective and have lost some of its properties. And maintenance also must be, of course, is essential, it is organized, and of course it has a cost. So here are some of the questions. It's not exhaustive, but some of the questions I would like you to address this afternoon in the light of the forthcoming example. And to conclude, I would like to let you think about this drawing. It's not mine, but I took it from the New York Times, from Doer, CWS, I don't know who he is, but he made a great summary of the situation. We have to make wise and sound choices for long term, not too early, not too late. And this drawing illustrates, for me at least, I don't know if you share this point, that some adaptation possibility can be done, but not all the things are possible. So just be aware and keep in mind that we have to define solutions according to the available resources. So this is the end of my introductory speech. If you want to contact me later, it will be possible, as Zim said, but here my email address. And I thank you for your attention.